Abderrahman El Farchouni will present some of his results of his research that he is carrying on during the PhD. In fact, he's a PhD candidate in hydrology and hydrogeophysics, conducting the research between the University Mohammed VI Polytechnic University in Morocco and the University of Florence. The research focuses on characterizing and quantifying groundwater recharge in data-scarce and semi-arid regions of North Africa, using integrated approaches combining hydrogeological investigation, environmental tracers, remote sensing, and hydrological modeling. The work aims to improve the understanding of groundwater system and support sustainable water resources management in vulnerable regions. So this subject is very new, is very important also for the connection with the policy for managing the groundwater resources. So thank you very much, and the floor is yours. And regarding questions, I ask those online if they have any questions to write in the chat, and then at the end we will try to answer. And for those that instead are here in presence, just raise your hands at the end of the presentation. Okay, thank you.
Thank you, Professor, for the introduction. Good afternoon, everyone. And thank you for participating in this seminar. It's my pleasure to present our work today before a distinguished audience. So, my name is Abderrahman El Farchouni, a PhD candidate from Morocco, working within the UM6B, the Mohammed VI Polytechnic University, and the University of Florence in Italy. So, this work is in the context of a cotutelle PhD between these both universities. So this presentation I have the honor to share with you today is entitled Characterizing and Quantifying Groundwater Recharge in Data-Scarce and Semi-Arid regions in North Africa, using multi-method approaches and water resources.
Is it the camera off?
Yes.
Is it a problem?
Yeah,
Does it work?
I have to go to meeting to.
Sorry, we are trying to switch off on the camera. Okay, go.
Maybe I have to sit. So the presentation is entitled "The Characterizing and Quantifying Groundwater Recharge in Data-Scarce and Semi-Arid Regions of North Africa using multi-method approaches and water resources implications." Before starting, let me briefly introduce the structure of the presentation. We will introduce first of all the hydroclimatic context of the North African region and Morocco, especially with the highlighting of main water challenges in this region. Then we will discuss the key challenges of groundwater recharge quantification in semi-arid environments. After that, we will present the different approaches used in this work, including field observation, remote sensing, hydrogeophysical investigations, and modeling. Finally, I will discuss the implications of these results for water resources management. Before going further, let me briefly introduce the institutional context of this work. This image shows the main campus of the UM6B at Ben Guerir. It's located in the middle of Morocco, we can say, near to Marrakesh, where part of this research is conducted. There is international collaboration agreement with the University of Florence, which is the context of my presence here today to present this work, which is the cotutelle and the cotutelle program between the UM6B and and UNIFI. So beyond research, the campus also offers an excellent environment for well-being with modern facilities and space designed to support both academic life and personal development. In fact, there is a current international possibility for a mobility as a mobility call within this agreement, offering an opportunity for students to carry out part of their research and maybe thesis, to attend also courses at the M6P. So the deadline for this call is tomorrow. If you are interested by this call, please contact Professor Giulio Castelli. So UM6P is mainly research oriented, but it is also a hub for education, innovation, and entrepreneurship, with a strong focus on sustainable development in Africa. Its activities address several key challenges facing the continent, including natural resources, management, and food security, sustainable industrialization, and human capital development. Within this framework, particular attention is given to water and agriculture, and also environmental systems, which are critical for addressing climate variability and water scarcity across many African territories and regions. The M6P has also gained a strong international recognition in recent years. In the Time Higher Education World University Ranking in 2025, the university was ranked in the 401 to 500 band globally in its first submission. And it is also the first in Morocco and the North African region. Also, we have the QS 5 stars rating, which recognizing the excellence in areas such as teaching, research, employability, facilities, and global engagement. And I think this achievement reflects the rapid development of the M6P as an international research and innovation hub, contributing to the African academic excellence. Now we go to the International Water Research Institute, which is the IWRI, is one of the key research institutes within the M6P, dedicated to addressing water challenges in Africa. Its vision is to lead integrated research and innovation for water and climate resilience across the continent. So the institute aims to deliver actionable science-based to deliver these many solutions to support decision-making in different areas such as water resources, management, food security, and climate adaptation. Its the structure of the institute is as follows: the integrated water resource management and climate change and adaptation, hydroinformatics and modeling, and water technologies and innovation. So let's start the scientific part about the groundwater recharge estimation to better understand this very important component, which is the groundwater recharge in this region. It is first important to start with and consider the hydroclimatic context of the region. As shown in this map, precipitation flow a strong north-south variability and gradient. So the rainfall is mainly concentrated along the Mediterranean coast and the Sahara. And the Mediterranean coast and for the mountain range, like the Atlas Mountains. Concerning the Sahara, receive a very low precipitation. It can be less than 100 millimeter per year. Concerning the mountainous areas such as the Atlas Mountain and the Rif Mountain in Morocco, for example, it's acting like the natural water towers, where higher rainfall and snow, like with the accumulation of snow, can lead to more recharging and feeding the groundwater recharge for the downstream aquifers through the discharge of rivers and through the direct recharge in the mountainous areas. So beyond this parameter of precipitation pattern, another important indicator is the aridity index, which represents the balance between precipitation and the potential evapotranspiration. So as shown in this map, most of North Africa is classified as arid to hyper-arid climate, reflecting very limited water resources and availability across the North Africa region. Only with the exception of narrow coastal area and the mountainous area, which represent more humid conditions. Overall, this highlights the dominance of dry and semi-arid conditions and climate across this region of North Africa. Focusing on Morocco, if we look more specifically, the country shows a strong hydroclimatic variability due to its geographical position between the Atlantic Ocean and the Mediterranean Sea and the Sahara Desert, combining with a complex mountain topography and plan, including the Reef and Atlas ranges. So as a result, precipitation varies significantly across the country, creating an uneven distribution of water resources, especially surface water resources, which the northern basins, like Lucus, Sebo, Melouia, represent only 7%, about 7% of the country's territory, and the other, in contrast, the other southern basins in the south represent the majority of the country's surface, experiencing much more limited surface water regarding the limit rainfall and the high evapotranspiration in these regions. And also the growing in population is another component that is important as a challenge and stress for water resources. Another important aspect of the Moroccan water system, which is the connection between snow and the groundwater, the connectivity between the snow and groundwater. So this is very important because many articles and many work was like find that the main source of water recharge is coming from the high Atlas and the high altitude area. So several major basins originate in the Atlas, where winter precipitation can accumulate as snow, and then like contribute to the groundwater recharge through direct recharge or through the recharge and the discharge from the rivers and also streams. Groundwater resources in many semi-arid regions are currently facing increasing stress. Surface water resources are often limited and highly vulnerable to evaporation and pollution. Also, we have which make like many sectors such as agriculture, water supply, and other economic activities increasingly depend on groundwater resources. In addition to this constraint, also the hydroclimatic constraint also play an important role, including the low and highly variable precipitation. So with climate change, we notice the variability in precipitation amount and pattern, and also the high evapotranspiration and the limited natural recharge. At the same time, intensive groundwater recharge and groundwater abstraction can, particularly for irrigation, have another component for the increase the pressure on groundwater systems. As you can see in the figure, this is some two piezometers from the Hazmjat aquifer, monitoring the situation of groundwater, which is currently in depletion, regarding all these components of that lead to water stress. Beyond this physical aspect of water scarcity, this groundwater is a key and fundamental have a key and fundamental role in a socio-economic system, particularly in semi-arid systems and region. In many areas, it represents the main and the primary source of drinking water and irrigation and other sectors. So groundwater therefore acts like as a key driver for the regional economic stability, especially under conditions of increasing climate variability. As a result, many sectors and communities have become increasingly dependent on these groundwater resources. However, unsustainable groundwater abstraction and use can generate significant economic and social risk, hydroclimatic stress, and declining of groundwater, which increase pumping cost also and energy demand. So this in turn rise the production and the cost of agriculture, reproducing farmers' profitability and increasing economic vulnerability. So over time, this pressure may also contribute to the growing inequality between water users and increasing social vulnerability. Ultimately, the water scarcity can affect several sustainable development goals, particularly those related to food security, clean water, energy, climate resilience, and inequality. And we talk in this situation. We are in the transition between water scarcity to economic and social scarcity. In this context of increasing water demand, limited surface water resources, and hydroclimatic constraint, sustainable groundwater management require a reliable estimation of groundwater recharge. This component, which is the key component, which is important for understanding the groundwater availability and also the functioning and the behavior of the system for the future, facing all this stress and challenges. It is essential to not only to define a sustainable abstraction limit, but also to designing effective aquifer management strategies, including managed aquifer recharge and other nature-based recharge solutions. However, estimation of this component groundwater recharge remain a major scientific challenge, particularly in this semi-arid region. This is mainly due to the scarcity and the strong spatial variability of the recharge, and also the difficulty to investigate some processes like snow melt contribution and the infiltration through the unsaturated zone, which becoming more and more with a high and very high thickness. To better understand groundwater recharge, we first need to look at the water cycle in the first time. In hydrology monitoring, this component is essential. This is essential to understand how water move from component to other component, and how water resources change over time. This include processes such as precipitation, evapotranspiration, runoff, infiltration, and groundwater recharge, as well as the interaction between each component and others. All these processes are summarized through a fundamental concept in hydrology, which is the water balance. This water balance is based in the mass conservation principle. So a fundamental principle guides our work. We cannot manage what we cannot measure or have a measurement about it. Therefore, monitoring the different components of the water balance is essential to understand how the hydrological system function, and to look. It's important to have some field observation and hydrological modeling using different instruments to monitoring the soil moisture, to monitoring rainfall, and other parameters. But we're still talking about a very limited. These observations are very limited and give information about point in the spatial, and they don't have a spatial distribution. And it's hard sometimes to access some places like mountainous region. It's hard to access and to get measurement in this in some areas. And also the conversion between specific point of measurement and the spatial distribution is very challenging, especially in area with a highly heterogeneity in the system. Well, the field measurements are essential and often remain spatially limited, especially in large or difficult to access region. This where remote sensing become a powerful complementary tool, using satellite observation to estimate the groundwater recharge. As you know, we cannot estimate this component directly from product, but we need to use each component, and through the water balance residual approach, we can estimate this component of groundwater recharge. And it is important in hydrology to validate this remotely sensed data and using in situ measurement. If we talk about validating this water balance or remotely sensed water balance approach, we should validate using measurement or using this method, which is the water table fluctuation. It's based first proposed by Haley and Koch in 2002. Is based on the monitoring of groundwater level, and then when the groundwater level is rise, we calculate the difference, the record of this rise, and using also the specific yield, we can estimate the groundwater recharge. Another widely used method to estimate groundwater recharge is the chloride mass balance method. This method is based on the conservation behavior of chloride in most groundwater systems, meaning that chloride is generally not effective by significant chemical reaction, like the component of chloride is not changing by chemical reactions. And when precipitation infiltrated into the soil, we have the process of evaporation, and the evaporation doesn't remove the chloride from the groundwater infiltrated, or the water infiltrated into the aquifer. So when precipitation infiltrated into the soil, evapotranspiration remove only water and not chloride. So this is why we consider as conservatively in most aquifers. So under the steady state conditions, the chloride input from the precipitation equal to the chloride output through the groundwater recharge. So we can use this simple equation to estimate the groundwater recharge through the chloride concentration in precipitation and in groundwater. So far, we have discussed different approaches to estimate groundwater recharge using different environmental tracers, etc., and observation. However, to fully understand the dynamics of groundwater systems, we need also hydrological modeling. In simple term, it's the model is a simplification of and it's a representation of the reality designed to reproduce the main processes that control the system. So the objective of the modeling is to understand how the system works and identify the key controlling parameters and simulate the future behavior of the system under different conditions and pressures. In this context, the role of a modeler is to simplify complex natural processes while preserving the essential dynamics of the system. So in hydrology, several types of models can be used to estimate this groundwater recharge. First, physically based models, which are based on such as mode flow, IWRI, free flow, etc., which simulate the physical processes governing water movement using equations derived from hydrology theory. We have also data-driven models, which include machine learning and all type of artificial intelligence approaches that can be directly learned from the data and give us and from the relationship between data set. Directly from this data set can lead to estimate. For example, if we need to estimate groundwater recharge using hydroclimatic variables, we can see if we have a correlation between variables and then estimate the groundwater recharge. So the last one is the physics informal neural network, which try to stay working with physical equations and also include the neural network to solve these equations and doing integrated between physics and the neural network. The first and I think the most important step in groundwater modeling is to define the question or purpose of the model. This means clearly identify what we need. Scientific or management questions and problem we want to address is related to pollution, is related to seawater intrusion or depletion in groundwater resources, etc. So we need to define at the beginning what the research question that we need to solve. The conceptual model is the second step, which is represents our understanding, the current understanding of how the groundwater system works. It integrates the main hydrological processes such as precipitation, snowmelt, infiltration, etc. And it also describes the physical structure of the system, like the geometry of aquifers, different type of flyers, and the type of aquifers, and also hydraulic parameters. In some areas, such as the mountain plain system, like the Atlas and the other plane related to the Atlas, we found like in Morocco, very case like that. The conceptual model must also consider processes like mountain block recharge, mountain frown recharge, and like the interaction between the mountainous area and the plains. This step is essential because it defines the framework on which the numerical model will later be built. So the conceptual modeling is essentially a simplification of the reality. We need this conceptual model because it provides a qualitative representation of the groundwater system, including the hydrological unit, system boundaries, input and output, input and the hydraulic properties, etc. So in many cases, it can be like seen as the hypothesis that about how the groundwater system behave. Because it just a simplification of some complex natural processes and it's a conceptualization of these processes. So to reduce the uncertainty associated with this conceptual model, it is essential to integrate multiple line of evidence and different type of data. In this section, I will present how several complementary approaches can be combined and lead to improve the conceptual model and the understanding of the aquifer system and the groundwater recharge. The framework presented here illustrate how different sources of information can be integrated to improve the conceptual model. And it's first, with the first study was the groundwater recharge potential mapping, which helped to identify the areas that are more favorable for groundwater recharge at the regional scale. The second work, it's about, or if we can say the second line of evidence, or using another type of data, using environmental tracers, such as stable isotopes and major ions, to provide another insight into recharge sources and the groundwater flow processes. Another one component, which is geophysical investigation and geological data, including field geophysical investigation, including also the geological data like logs and cross-section, etc., to characterizing the aquifer, the aquifer geometry and the subsurface structures. In addition, the remotely sensed approach allows us to estimate the key water balance components, such as precipitation and evapotranspiration, etc. Finally, this different data set can lead to be integrated within the hydrological modeling framework using SWAT and ModFlow to simulate groundwater flow and recharge processes. Together, these complementary approaches help to reduce the uncertainty and to improve the reliability of groundwater recharge activation. As the first component of our multi-method framework, we develop a groundwater recharge potential map to identify the areas that are more favorable for groundwater recharge at the basin scale, which is the intensive basin. So the approach is based on the integration of different parameters of several thematic layers that influence groundwater recharge, including land use, land cover, rainfall distribution, linear density, lithology, drainage density, and the slope. These variables represent both hydrological and geological controls on infiltration and the groundwater recharge. By integrating all these parameters, the spatial data set, we obtain the first regional indication of where recharge are more likely to occur within this basin. So the methodological framework used to generate this map, this recharge map, is illustrated in this figure. We find different data sets, as we said, are collected, are processed, including remote sensing data, meteoric data, observation, digital elevation models, and geological maps are used. From this data set, several thematic layers were derived, such as land use, land cover, rainfall, etc. These layers were then integrated within an AGIS environment, and used to through the analytical hierarchy processes, which are seen for each component and white to based on its relative importance for this groundwater recharge. And finally, the resulting recharge potential map was validated using stable isotopes, providing independent evidence to support the spatial recharge pattern. Concerning the study area is located in the intensive basin in Morocco, focusing particularly on the Piedmont zone between the High Atlas Mountain and the House Plain. So this region play an important role in groundwater recharge because the mountain area acts like the main water sources for the downstream aquifers. So we have like the climate is semi-arid with annual rainfall ranging between the 340 and 50 millimeters per year. So the resulting map divided the study area into 5 main groundwater recharge potential classes. We have ranging from the very low to very high zone. So the results show that the moderate recharge zone are dominated the basin covering most of the alluvial plain area so we have another zone with a high recharge potential are mainly located in the High Atlas Mountain and the Piedmont zones, where recharge like enhanced by higher rainfall, snowmelt, and stream infiltration. So in contrast, low recharge zone correspond mostly to urbanized and area and low permeability geological formations. Finally, the very high recharge zone are limited and localized generally associated with the high mountain areas and spring. To validate the recharge potential map, we used stable isotopes of water, particularly oxygen 18 and deuterium. So this figure on the left show the relationship between oxygen 18 and deuterium compared with the global and local meteoric water line. So the mass of groundwater samples plot close the line, indicating like the groundwater recharge are primarily derived from meteoric water origin, meaning the rainfall and snow origin. So the figure on the right relate the oxygen 18 values to the recharge altitude using the local altitudinal line. So this relationship allow us to estimate the elevation where recharge occur. So the results suggest that groundwater recharge mainly originated from the higher elevations in the High Atlas Mountain, which is like consistent with the recharge zone identified in the analysis in the spatial analysis. And the results of this work were published in the Journal of Scientific African. If we can say as a second line of evidence and another component, we investigate groundwater recharge processes using hydrochemical analysis and stable isotopes. The study combined field of measurement, laboratory analysis, and hydrogeological informations to better understand like the groundwater origin and flow dynamics. So water samples were collected from well springs and also surface water, and then analyzed for major ions and stable isotopes. Then hydrochemical data were processed using a different approach of multi-statistical analysis, including hierarchical clustering, principal component analysis, and self-organizing maps, etc., to identify the hydrochemical phases and dominated the geochemical processes in the region. At the same time, like isotopic analysis were used to estimate recharge altitude and identify recharge sources and period. With all of this data, we need this study to improve the conceptual model. We have also the hydrogeological side of this work, which based on the piezometric maps and geological maps to have like the hydraulic head based conceptual model, and then to combine the hydrochemical and isotopes conceptual model with the hydrogeological conceptual model. To investigate groundwater recharge mechanism, water samples were collected from groundwater wells, springs, stream, etc., and snow also, covering the system from the high altitude in the high Atlas Mountain to the House Plain. So hydrochemical analysis and for major ions were performed at the laboratory of applied geology and geoenvironment in Agadir. In addition, stable isotopes of water, especially mainly oxygen 18 and deuterium were analyzed at the IWRI laboratory using the cavity range down spectroscopy. So these images illustrate path field sampling combine the field and the sampling combine, and also the laboratory analysis. So as another line of evidence, we used hydrogeophysical investigations to better characterizing the aquifer structure and hydraulic properties. Two main techniques were applied in the field, which is the resistivity tomography, the electrical resistivity tomography, which provide the two-dimensional resistivity variation and of the subsurface. This method can help us to identify the aquifer geometry, the geological layers, fault, etc., and also the potential recharge pathway. The next step in the modeling is, as you know, in many studies, the process of the modeling is treated only as a final product. Data are given to a modeler, a model produced quickly this model and delivery. However, groundwater system is very complex, and this approach is lead to large uncertainties. Instead, the process, the collective learning process is very interesting, where during this process, discussions, DART, and etc., we can have mini discussion between data and model results, between agencies and scientists, etc. And also they can help us to identify the missing information and to improve the conceptual model and to refine each parameter. So one of the most powerful idea in modern science is the bias theorem. In simple terms, the bias theorem tells us how to update our knowledge when new data become available. So it combines two sources of information. First, what we already know, which we call the prior knowledge, and the second, the observation or the measurement, which represent the data. Mathematically, Bayes' theorem updates the prior probability using likelihood of the observed data, producing what we call the posterior distribution, which represent our improved knowledge about the system. In groundwater modeling, this framework is extremely useful useful, and often we start with expert knowledge and geological information such as pumping test, stratigraphic logs, and etc. of geological information. This represents the prior information. Then we integrate hard data such as hydraulic head, pumping record, weather data, or the river measurement. By combining these two sources of informations, we throw the Bayesian inference that can allow us to estimate parameters like transmissivity, hydraulic conductivity, and other aquifer parameters. In other words, the model is not fixed. It learns from new data, from new measurement, and become progressively more reliable. After defining the conceptual model and integrating different sources of data, the next step is selecting appropriate mathematical model and numerical code. So we choose the model and the numerical code, and it depends the complexity and the objective of the study, and also it depends on the problem and what we need to solve as a problem. So we choose analytical solution. If we have a simple problem, then we have numerical models and the hybrid modeling framework integrating physical approaches and also data-driven models. In groundwater studies, like several numerical codes are commonly used, such as ModFlow and FFlow. So once modeling code is selected, the model design phase begins with including defining the model domain, boundary conditions, and other parameters. So concerning the calibration, before discussing this very important step of calibration principles, it is useful to a little bit discuss how groundwater model work. A model first time can build with a structure which define physical geometry and also boundary conditions, etc., for the structure of the model. Then we define the input such as recharge, pumping rate, or fixed hydraulic head, because we need it for the steady state model. Finally, we assign the parameters that control groundwater flow, such as hydraulic conductivity or storage coefficient, etc., with the structure and the input parameter are provided to the model. So these parameters, we need to talk about it, because we try to change different parameters to fit our model and to reproduce what happened in reality and what happened in measured data in the field. So this is we need to talk about this principle of parsimony, which is very important, and I think is very important in this step of calibration, and it's related to the philosophy of Occam Razon, which entities should be not complicated or multiple beyond the necessity. We have a limit we should to respect. In groundwater modeling, this means that the model should remain as simple as possible to reproduce the observed behavior of the system, of the aquifer system, increasing the number of adjustable parameters, often improve you see in the figure. We can improve the fit between measured data and predicted data by increasing the number of parameters, but at some level, the increasing of parameters doesn't mean we are fitting very well the model, but it can be related to a noise or overfitting. So as a result, prediction reliability may actually decrease even though the calibration error becomes smaller. So a good model is not necessarily the one that fits the dataset best, but the one that explains the system with the minimum number of parameters and supported by the data. The second role of principle of parsimony concerns the parameter correlation, which is one of the main difficulties in inverse modeling. Yeah, we use two parameters in these figures. We have we try to calibrate with two parameters, which is the recharge. We change in recharge, and also we change recharge and hydraulic conductivity. So if we have a hard correlation, we have a hard correlation with the coefficient equal to 1 with both parameters. We have a problem of no uniqueness solutions, and we have a limited combination between each component. If we change recharge, we have another solution, so we have a limited solutions. So these parameters are very correlated. If we change a parameter, it can give a similar effect on the simulation and the model result. So increasing recharge, for example, or decreasing hydraulic conductivity, it can give the same result. In this case, like our model cannot like distinguish which parameter is responsible for this change in, for example, in water level. So we need to regarding this principle of parsimony, we cannot like calibrate a model using two parameters that are very correlated between them. So we work only with one parameters, or we can also use an additional independent data set to constrain this correlation between both variables. So another aspect, and I think it's the last in the part of calibration, which is sensitivity analysis, which measure how like much the model output change when parameter change. In other words, it tells us how strongly the model results like respond to the specific parameters. So we cannot simulate a model with all parameters. We need to use this sensitivity analysis and to work with only with parameters that are that the model are sensitive to these parameters, and avoid parameters that are not sensitive to. After calibration, the next step is the model validation and the uncertainty analysis. First, we evaluate how well the model reproduces the observation by comparing like the simulation and what we get as what we have like as a measurement data, such as groundwater levels, stream flow, or recharge. Model performance like typically assessed by using statistical indicator such as RMSE, NSE, or R square, etc. So when possible, it's possible to use independent data set to validate our simulations. So, however, even a well-calibrated model still contain like uncertainties. We have also to mention our uncertainties of our models. This can be related to the data limitation or like parameter estimation, or also the conceptual model. So to estimate the groundwater recharge realistically, we need to represent the entire hydrological cycle from rainfall to groundwater flow. So this surface processes such as precipitation, evapotranspiration, runoff, and infiltration are simulated using the SWOT model, which provide the spatial distribution of recharge estimation. This recharge flux are then used in mud flow, which simulate the groundwater flow within the aquifer. And we have like the coupling. We have two approaches that can be used for this coupling, using the one-way coupling, where like the SWOT simulate the surface processes and give mud flow component such as a recharge, and then simulate mud flow for the groundwater flow processes. And we have like a fully coupled method, which both models, SWOT and mud flow, exchange flux and at each time dynamically. So in this framework, each model represents a different part of the system. SWOT like simulate the surface hydrological processes estimation, and estimating like runoff, evapotranspiration, soil moisture, and recharge. And mud flow can simulate like groundwater flow, including hydraulic head, aquifer properties, and pumping, etc., and other components of the groundwater flow model. So by combining both models, we can link surface processes with the groundwater dynamics, improving the estimation of recharge and water resources management. So in recent years, as you know, like data-driven approaches and models are becoming very useful, especially machine learning and deep learning have become increasingly important in our domain. So this, in first hand, they can improve the model input. Even if we use a physical-based model, we can use data-driven or AI model to improve our input for this artificial and for this physical models by estimating like missing values or by uncertainty by using like estimating some parameters. For example, they can construct groundwater level and time series and to estimate, for example, precipitation, for example, evapotranspiration, and we can use it to doing like down scaling of different parameters. Second, like the machine learning and artificial intelligence in general can support parameter estimation by identifying like the relationship between hydrological variables, helping to estimate like different parameter of the hydrological system. So finally, the hybrid approach is becoming also increasingly important in our domain, using the data-driven models with physical models, and this is include the coupling of, as we see in the other slide, we do coupling with physical law with neural network to try to solve these equations, and this is already very useful for surface water fluid, etc. to simulate, for example, and to solve, for example, Navier-Stokes equations for simulating stream and canalization fluid. So to conclude, I would like to highlight a few key messages from this work. So first, groundwater recharge estimation highly uncertain, have a highly uncertainty in semi-arid and data-scarce region. So the understanding of this recharge processes, therefore, need to integrate multiple sources of data and evidence. So we need to apply this interdisciplinary approaches. The second thing is the multi-method framework significantly improve our ability to characterizing the system and to quantify the groundwater recharge. So by combining this field observation, environmental tracers, remote sensing, etc., and other methods, we can obtain a more reliable understanding of groundwater system. And also the conceptual model should be not considered static, but must continuously evolve as new data are available. And using the Bayesian approach, updating and data assimilation can allow us to progressively refine our model and reduce the uncertainty. And the fourth point is the transparency and communication are very important for effective water management. Clearly, communication and communicate models, assumptions, and uncertainty can help to build a trust between different scientists and managers, and decision makers. And finally, sustainable water management cannot rely on science alone. It also requires integrating local knowledge and engaging stakeholders, ensuring that management strategies can realistically and also to adapt strategies for social and to be acceptable. So I like to summarize here some take-home notes, which is groundwater recharge estimation remain highly uncertain in semi-arid data-scarce region. Understanding of this recharge require integrating multiple sources of evidence and interdisciplinary approaches. Second point is the using of multi-method framework to improve the characterization and the quantification of the groundwater recharge, combining field observation, environmental tracer, and all this method. So conceptual models must continuously evolve as new data are become available using, as we say, the Bayesian and the data assimilation. Also, the transparency and communication are very important for effective water management, and we need also the sustainable water management, require the integration of local knowledge and the stakeholder participation. And in fact, I like to finish my presentation with this quote: when the fact change, I change my mind. And also the models. We change the models, conceptualization and the parameters when we have a new data set. Thank you for your attention.
Okay, so thank you very much. And maybe it's a little bit advanced. I don't know if for some of our students this application of the models could be a little bit not a new subject, but maybe you are not so familiar. But that doesn't matter. I think it's always understandable and see the potentiality of this kind of instrument for management of resources, and as we saw, both surface and groundwater. So first of all, if there are any questions from the audience. And check if there is anything on the chat. Oh. Okay, so we have a lot of questions from remote, so we will start with that. And if you have anything, just let us know.
Until now, this is AI assistant.
I liked very much in the last slides the importance of the stakeholder involvement, as we have already pointed out in our lectures. So it's not my voice, but it's a general voice, the involvement of the stakeholders. Okay, so...
Okay, maybe we can start with this question in the chat related to the mobility. Can you please put the link or some information about the mobility you mentioned here? So regarding the mobility, I don't have like a big about any information about this, but you can contact Professor Giulio Castelli and you ask him about this mobility. But what I know, this mobility is you can't. What you can do is, for example, the thesis. If you need to have a mobility of a thesis research work, or even for courses, if someone need to have some courses in the EM6P in Morocco. I don't know if...
I can add that if he or she goes to the UNIFI website and can find for sure information about Erasmus Extra we call, or just Google it. So, or just remember that deadline is tomorrow, and there are some documents to be prepared. So.
A lot of people asking about information about this mobility. I think it's clear. The idea it's clear. You can find it in the website of the UNIFI. Concerning this question, what limitation or uncertainties prevent generalizing our finding regionally? To respond this question, first of all, we have a different type of parameters of geological systems. If we talk about local system, it's not like the same behavior like the regional system, and the complexity. This can lead to the complexity and the heterogeneity of all parameters that are talking about. For example, for groundwater modeling, if we're talking about hydraulic conductivity. It's very variable in the regional, in the local scale, not in the regional scale. So this variability is very high. So this is why the uncertainty is becoming very high when we talk about the regional distribution of the studies. Okay, there is another question. Thank you for the presentation and this interesting topic. How was connection between surface water and groundwater represent the modeling framework? Was groundwater coupled with the watershed or rainfall runoff model, or were recharge and stream interaction introduced through boundary conditions? First of all, we have like boundary conditions to define, and we have like recharge from the stream. We have like direct recharge from as like the component of the recharge, like we use in the mud flow model. But the rainfall runoff is as a model using SWOT. We do this kind of modeling to estimate the runoff from rainfall, but not only runoff. Using SWOT, we can also estimate the percolation, the deep percolation. And this deep percolation is also important and interesting for mud flow. This is why we integrate both models to simulate what happened in the surface processes and what happened as evapotranspiration, surface runoff, etc., to combine with the mud flow. And this recharge from the SWOT mud flow, the SWOT can be used in mud flow as an input to estimate the groundwater flow dynamics. And we have like, this is the direction workflow, but we can have the both side. We can like have like interaction between both models.
I have one question.
Okay.
The question is the following. Do you think that this coupling of surface and groundwater modeling that you applied in this watershed in Morocco can be also transferred to other contexts? So do you think that, first of all, for answering for the possibility of transferring, you have to check, obviously, the availability of data and how you are dealing with this limitation in sometimes the unavailability of data.
I think it's very interesting in many other regions, which is we have like a mountain region are very important in groundwater recharge, and this connection between cryosphere, which is considered the mountain, and the PEMO region. So this the integration between and the investigation of cryosphere groundwater interactions using SWOT and mud flow, it's very interesting. And this case of cryosphere groundwater interaction is we find it a lot of and very not very well investigated. So this model for sure can be like used in other region, but with different parameterization, with different approach for the modeling. And for sure we have to consider each specificity of each region regarding the geological formations, regarding the structure, etc. Concerning the data availability, we try to, this is why we try actually to combine remotely sensed data also with some measurement data, and we do in our institute the necessary field work to complement what we have like as data from the agencies, and we have like collaborations with them to get the data, etc. And we try to combine all that we have like as data and also with the remotely sensed data to more estimate each component as for the inputs of the model.
Another question that I have is, do you think that this kind of simulation would be a powerful instrument for a policy, for example, protection of recharge areas and so on? Do you see an application in real life going to the policy makers and then say,
okay. For concerning this point, it's very important because after modeling, what we need to solve using these models, for example, if we quantify and characterizing groundwater recharge, what we need to solve. Actually, we have like the first thing is the managing of the distribution of farmers, for example, distribution of new project of farming. If we have like a area with allow groundwater recharge and limited water resources and very high vulnerability to drought. So we should not like make a new project for example, for agriculture, and also to have to make another nature-based solution to enhance and to improve the groundwater recharge. The natural groundwater recharge by integrating like managed aquifer recharge, by constructing dams like we find in Morocco. A lot of dams are now constructing, but as you know, surface water are very vulnerable to evaporation and also pollution. So groundwater is still very important and interesting. So we can discuss with the stakeholders and decision making to make more projects and to enhance the groundwater recharge using different approaches, and also for the land use. Sometimes the land use is very impacting the behavior of the system, and sometimes the deforestation can lead to increase in groundwater recharge rate. So if we can talk to decision makers to make this in consideration, it's very useful. So in our model, we can have this scenario simulation to see if we apply this strategy, how the system can behave, and if we apply this constraint, how the system can behave. So this is very interesting also for decision makers to have like these models as a tool for taking some decisions.
Okay, so thank you. I think there are in the meantime some other questions.
I have a question here in the chat. Could you please indicate the approximate depth to the groundwater table in this study area? Actually, in some study area, the water table is very depleted. I will show in the. I have some. So this is the water table declining, but this is not the worst case. I think this is not the worst case. We have like a water table more than 200 meters in the region of the house. So the situation of all the majority of piezometers in this aquifer of the house is like that. We have like a big decrease in the level. Do we have any questions?
No questions, no curiosity, no. So if not, we thank you very, very much for the great job you did. And I know that you are leaving in some days, by the end of March.
Yeah.
Okay. But you will come back next September.
Maybe October.
October, yeah, because he's having the cotutelle, so it has been said at the beginning, he will be supervised by UM6 and University of Florence with the Professor Castelli. So that's why with the cotutelle he has to spend at UNIFI one year. So 1 year divided into 6 months and then 6 months. So thank you very much. And if in the meantime this subject could be of your interest, just let us know, because it's something on which the Water Harvesting Lab is working on. Obviously, the case study has been analyzed and proposed by Abderrahman, because it's a PhD work. But obviously, if you would like to switch to this subject of modeling, hydrological modeling, or groundwater modeling, just let us know. Okay? So thank you.
Thank you very much. Thank you very much. Bye bye.